Welcome to my presentation about the Age of Chaos library. I apologize for not showing my face, but I couldn't manage to actually find an easy way to record both my screen and the camera. So the Age of Chaos library pretty much puts together about 15 years of my research on feedback systems and complex adaptive systems. So it is a library specifically designed to implement complex adaptive systems, but I believe that it can be useful for users in general, for more general applications, because it has a lot of functions that can be used in any context. The main reasons why I'm interested in complex adaptive systems, I've written a lot about this, and I will be brief about these reasons, but it's basically that I do believe that complex adaptive systems for music, they're extremely powerful to develop new musical ideas and new musical aesthetics. So I find it that it's a great way to explore new music live in this case. And there are some advantages that I consider particularly important. One of them is, for example, the fact that you can achieve high musical complexity while you have a low CPU requirements, which is not always the case, for example, with neural networks. And it has a kind of expressiveness and organicity which is particularly good for the musical domain, I believe. And what I think is that when you put together artificial intelligence and human intelligence, it's like artificial intelligence in this case, it should be like an extension of human aesthetics. And what I found is that when I let my algorithms perform for me, I actually achieved my aesthetics better than I used to do when I was performing actively. So many of my works are based on autonomous systems that I trigger with some initial condition, and then I let the systems do most of the things, except sometimes when I try to perturb them in some ways. And the reason why I chose Faust to implement my systems is because before this I was using pure data, but I was using just the DSP aspects of pure data. I was never using message domain, so everything was signal. And Faust was just the natural choice because everything is signal in Faust, and it was necessary for the implementation paradigm that I was using, which is that of time variant nonlinear audio feedback networks. So my systems are usually feedback networks with different nodes, each of them doing a number of tasks, and they are interconnected through feedback loops. And there's a lot of nonlinearities in between. And the other paradigm is that it is based on what's called agent-based modeling. So each of the nodes, each of these agents is actually a complex system itself, with an information processing network combined with a sound processing network. So each agent is analyzing the coming signals. Information is extracted, and based on this information, the processing algorithms are piloted to create positive or negative feedback loops. So imagine a network with a number of agents. So you can imagine why these systems can achieve complex behaviors. And the most important aspect of my library is probably the information processing algorithms are some of the most important, I believe, because the other ones are not particularly original, perhaps, and they're not as relevant as these ones. So for the information processing, I developed a set of original time domain algorithms for the extraction of information. So I was kind of forced to do time domain algorithms because there's no FFT in Faust, and I'm completely happy with that. And it was interesting because I actually had to find ways to perform this kind of processing with time domain algorithms, and it resulted in CPU efficient and sometimes even more accurate algorithms for the extraction of information from audio signals. So if we look at all the library modules here, we have, this all EOC is just to import all of the main modules, and then we have auxiliary is some auxiliary functions to see if you it should simplify the debugging and testing. Delays is just Faust delays, but with sample rate independent parameters, and then this is Edge of Chaos is just the same as Faust, std faust.lib, so it's just loading all the environments. Filters has a number of filters, among which we have the zero delay feedback topologies, which are stable for cutoff modulation, and that's useful. And then information processing, we have some low-level and high-level information processing algorithms that we'll see in a little bit. And maths has a lot of mapping functions, and then there's number sequences that I sometimes use as an alternative to the prime or coprime number list that we use, for example, in feedback delay networks, and for other reasons similar to those. And then in oscillators, we have mostly oscillators that are used for band limited synthesis, but they are some of the oscillators actually require a little bit more work because the DC compensation algorithms still don't work as good as they should. So for this, I mean, they have the most accurate spectral response, the number of harmonics, and the spectrum of the band-limited oscillators in my library actually seem to be the most accurate compared to Faust band-limited oscillators, but Faust oscillators are still more stable, and I would suggest to use those. And outformation is, I call it outformation, but it's basically sound processing units. So you can have reverberators, there's pitch shifting or time stretching, and there's ground synthesis techniques, some of which are original, and I will also show this in a bit. And it's just processing units to transform the incoming audio signals. And then the stability module is what contains bounded saturators. There's look-ahead limiters, and there's adaptive algorithms for automated gain control. So this is basically necessary when we implement feedback networks. In some cases, I also work with self-oscillating systems, so we have to take care of stability, and this is a way not to let things blow up. And well, as an example, I was saying there's one of the algorithms that might be new and useful for other things is this thing that I implemented is a zero crossing synchronous granulator. And it's basically, rather than using overlap add to one techniques where grains are overlapping and they are windowed to deal with discontinuities and then they're overlapped. In this case, what I'm doing is to perform an analysis of the input signal to record all the positions of the input signal on delay lines where a zero crossing occurs. And the main mechanism is that when we have a desired grain duration, so after the grain duration has passed, if the output of the granulator is at the zero crossing point, then we can trigger the next grain, which starts at zero crossing point. Of course, we want to take care of continuity and differentiability as much as possible to reduce noise. So in this case, we are taking the analysis that I'm performing, which I believe is enough for this kind of application. It does introduce some noise, but for the musical application, I think is good enough. And it's, of course, it's a trade-off between accuracy and efficiency. In this case, I'm performing the analysis of first order and second order derivatives to make sure that the last grain derivatives are compatible, or there's continuity in the signs of the first order and second order derivatives at the junctions. And this was a good result for me, while the CPU requirement was not particularly complex or high. And so there's also, of course, a correction function that is necessary because sometimes we may transition from fast rate grains to slow rate grains. So the zero crossing is not always at the same position. So it may be that, for example, if we have a look at this, it might be that this is a fast transition and then we have a slow one. So it can be that the zero crossing from this point to this point is here, whereas if we trigger the next grain, it might be that the zero crossing is from here to here. So it will still jump from this point to this one. So we will have an inversion of sign and this will result in a click. And the most important thing of this granulator is that it can be used, depending on the parameters, as a multi-mode system for click-free looping. It can be a wavetable oscillator if the grain rate is high enough, and it can also be just an asynchronous granulator where we trigger grains with random positions and pitches, as in this example. And the good thing, of course, there's some noise that is introduced, but the good thing is that, for example, we don't have the artifacts of overlap at 2-1 techniques where we have the typical comb effect that is not desirable for my personal taste, at least. So here we can see, for example, when here we have a generated sine wave. This is slightly less than 1K, and the grain rate is 197. I chose these two numbers as non-even fractions so that the period of the sine wave will not be synchronous with the triggering of the grains. So this way the algorithm actually has to do some work and wait for the signal to be at the zero crossing before the next one is triggered. So this is the original one, and this is the reconstructed sine wave. In this case, we have 197 uncorrelated grains per second. So each grain is taken from a random position in the buffer. The buffer, if I'm not wrong, is about 10 seconds and 96 kilohertz in this case. And here we can see a sawtooth wave. This is the original, the ideal one, and this is the same signal which is being shuffled and reconstructed. And here we can see how much noise we are introducing. Then if we jump to the information processing algorithms, one of the most important one, I believe, or perhaps one of the most effective or relevant algorithms I've written is this adaptive spectral centroid algorithm. So this is it is computationally pretty efficient, because here we have this is a first order crossover. So it's a low pass, well, 1 pole 1 0 low pass and 1 pole 1 0 high pass. Besides, with first order filters, we can implement a crossover with a multimode topology. So we can just calculate the low pass, and then the high pass can be calculated as the input minus the low pass output. And that's quite efficient. In this case, we have the RMS calculation is just using 1 pole low pass filters for the averaging. And then we have, there's an integrator, and here it's not showing, but it's a good idea to actually clip the output of the integrator between 0 and 1, so that the frequency that is sent back to the crossover is not exceeding the allowed frequencies for the filter. So in this case, we have the input that is divided into two spectra, the low spectra and the high spectra. We are taking the difference between the high one and the low one. So based on this imbalance, we are shifting the frequency of the crossover so that the frequency we find, the system automatically finds a frequency where the weight of the two spectra is roughly the same. And this is a normalization factor that is used to have a response that is independent from the amplitude of the input. And this nonlinearity is particularly useful when we use very high analysis rates. So it's basically, since this is a negative feedback loop, we'll have an oscillation around this equilibrium point. So it's a balancing point. And this is the kind of response that we can see. So this is from time 0, we start the system. This is at 15 Hertz analysis rate, which means that the low pass filters have a 15 Hertz cutoff, and then the integrator, this is just one sample full gain feedback loop, and the input is multiplied by the angular frequency at 15 Hertz. And we can see that this is a 1K sine, and after about 0.06 seconds, which should be the expected analysis rate or time of analysis, we have a value which is close enough, and then it stabilizes, and as you can see, it's fairly accurate and stable. And in this case, we have noise at 96 kilohertz, so this is about half Nyquist, which is what you would expect as the spectral centroid for this signal. And then the other relevant aspect in this module is the high-level audio information processing units, which are based on the state space analysis of low-level information signals. So, for example, low-level information signals, we're talking of spectral centroid, we have noisiness, or we can have roughness, or even the RMS if we want to analyze the intensity of a signal. And we have these three main high-level information processing algorithms. Dynamicity is essentially giving a rough estimation of how fast the low-level characteristics are changing over time, and we are accumulating the magnitude of these differences. And we are accumulating them non-linearly because the contribution, of course, is not linear. When we have more signals that change all at the same time, it doesn't mean that that is linearly multiplied. So the tan H function seems to be a good approximation of what the perception seem to be like. And we then have the heterogeneity is based on an algorithm that it's just taking the average absolute deviation. It's a normalized version of the average absolute deviation, so that if the signal is in, let's say that we divide the low-level signal in perhaps 10 states. If we have a low-level signal which goes from 0 to 1, we divide it into 10 smaller regions. So point 1, point 2, point 3, and point 4, point 5, and so on. And if the signal is entirely in one of the 10 bands, we have the output of the heterogeneity is 1. Otherwise, if it's homogeneously distributed over the whole 10 bands, we have a heterogeneity index which is 0. And this is roughly telling us how chaotic a signal is. So the higher this number, the less chaotic, because the signal is orbiting a smaller number of states. Whereas if the signal is really homogeneous, it means that it's going through a lot of states and it's more likely to be chaotic. The complexity, on the other hand, is an oscillation in the heterogeneity index of the signals. And what seems to be a very important aspect of this work that I've been doing on this library is the future of the library itself, because my plan now is to actually turn it into a complex adaptive system automatic generator. So the idea is to follow the same paradigm as Kaufman's random Boolean networks, where we have network structures and organizations which are determined by randomness, but the network itself and the behavior is entirely deterministic. Because I should point out that all of my systems are entirely deterministic. There's no randomness or pseudo-randomness in the audio signals and information processing. So for example, my idea is in the foreseeable future, I would like to see this library to turn into a function such as this one, where we give an integer for the order of the network, an integer for the order of each agent. Then we have a SID, which is a unique identifier combined to these biases, which are used to model the behavior of the system. So if we have an nth order network, we have n inputs and we have n outputs. Then we have each agent with a inputs. So each agent will be combined by a processing units, which are combined together to produce an output. And within the agents, of course, there will be an information processing infrastructure that will be used to extract information and then pilot the variables of the transformation processing units. And all of these units will be determined randomly by this seed. And we'll have a network that is made up of n times a feedback loops. And all those feedback connections, of course, are also determined randomly. So we will have a huge amount of topologies that can be explored in this kind of configuration. And this biases, the seed is going to feed a number of uniform pseudo-random generators, but then we will use biases to change the probability distribution, and this probability distribution will be informed by musical parameters. So we'll be able to say if a system will be should be more rhythmic or less rhythmic, more or less abstract, more or less noisy, for example, and or if the evolution rate should be fast, so how dynamic the system should be. And this is essentially it. So I will keep it short because I actually have no idea how long I've been talking, and maybe we will leave some space for the live Q&A. So the last thing, if you want, you can check one of my pieces, which is entirely realized in Faust using the library. And this is just this recording is just the impulse response of the system. So I've designed the system, and then I've triggered it with a Dirac impulse, and then it is entirely autonomous. There's no human intervention, and it's a closed system. It's self-oscillating and it's closed, so there's not even external perturbations changing the system. It's all on its own. Everything is on its own. And here, for references, you can still see my websites, and the library is freely available, and it's released under the GPL2 license. And thanks.